Hi, everybody. Thank you for coming. I'm truly honored to receive this award on my dissertation called Optimization Methods Based on Decision Diagrams for Constraint Programming, AI Planning, and Mathematical Programming. And this thesis was supervised by Chris Beck and Andres Sire. So first, I want to talk to you a little bit about decision diagrams, and I'm going to explain them using this little example. So decision diagrams are graphical encodings of the solution sets. That's how we're going to interpret them in this work for discrete optimization problems. So basically, there are layered directed acyclic graph with a root node and a terminal node. We have one layer for each of the decision variables, and the arc labels represent the values of the variables. So in this case, dash arrows represent xi equal to 0, and solid ones represent xi equal to 1. So what we have here is that we have for each root to terminal node path, we have a complete variable assignment, as we can see here in the example. And we say that we have an exact DD if we have a one-to-one relationship between the paths in the graph and the solution set X. And we also say that we have a relaxed DD if the paths in the graph are actually a superset of the solutions of X. So the main advantages of these graphical encodings are their versatility. Specifically, we can use them to represent the solution set of many complex problems. Also, they're compatible with existing discrete optimization techniques. So this leads us to the following thesis statement. Decision diagrams are effective tools to capture complex combinatorial structures for discrete optimization problems that are not fully exploited by general purpose solvers. Thus, combining decision diagrams with existing methodologies can achieve a state-of-the-art performance on challenging optimization problems. And to tackle this thesis statement, we have 3 projects in this dissertation when we show novel DD-based techniques and apply decision diagrams to new challenging problems where decision diagrams haven't been applied before. The first project is a multi-commodity pickup and delivery problem where we combine CP, DD relaxations, and Lagrangian duality. We also present a new way to construct decision diagrams based on the capacity constraints of this specific problem. And also we achieve a state-of-the-art performance. And this work was published in the Informs Journal of Computing. The second project is on delete-free AI planning, where we propose 2 DD-based admissible heuristics and relate them to existing heuristics in the literature. And we also compare to MALP alternatives. And this work was published in ICAPS and also in JER. And the last project is cut generation and lifting for binary optimization problems, where we use decision diagrams to do these 2 procedures. We apply them to chance constraints, and we also achieve a state-of-the-art performance. This was published in Mathematical Programming very recently, and it won 2 student paper awards, first place in the Canadian Art Society competition, and second place in the Informs Computing Society competition. So now I'm going to explain the first project, the multi-commodity pickup and delivery one. So this problem is very simple. We have M-distinct objects that we have to pick up and deliver, which basically will impose some precedent constraints between the visits that we do. The objects have a certain way, and we have one vehicle that has a limited capacity. And the main goal is to visit each location once in a single tour, such that the total distance is minimized. So to tackle this problem, we use a relaxing DD representation. So the main idea is that we're going to have one path for each feasible tour, and some of the paths might be infeasible. So here, for this specific example, here is the MDD, and we can see, for example, that if we take this specific path, it's actually the optimal solution if we consider the traveling distance here in the network. But if, for instance, if we compute the shortest path over the decision diagram using the distances again from the network, we actually get an infeasible tour because we visit location 5 2 times, but we get a lower bound. And this is how we're going to use the relaxed MDD as a lower bound procedure. To construct these decision diagrams, we have an iterative algorithm that has 2 procedures, a filtering one that basically identifies infeasible arcs that are corresponding to infeasible solutions, and a refinement procedure where we split nodes until we reach a size limit, in this case the width, the number of nodes in each layer. In particular, we propose a novel filtering rule for the capacity constraints of this problem, and we have 2 different refinement procedures, a tour-based one that was in the literature, and a capacity-based one where we show that we can simplify this capacity constraint that was very challenging for this problem, only using C+1 nodes in each of the layers of the decision diagram. In addition, we want to strengthen our DD relaxations using linear constraints. And how we do this is that we introduce them as dual information to the decision diagram. So what we're going to do is that we have our a normal objective function, but we're also going to add some penalties when we violate certain constraints on the path of the decision diagram. And to find the optimal coefficients, what we do is that we solve the classic Lagrangian dual problem, where we basically iteratively propose a new Lagrangian penalties, and the sub-problem is basically a shortest path problem over the relaxed decision diagram. So it can be solved very efficiently. So all in all, how do we solve this problem? We basically have a branch and bound procedure embedded in a CP solver where we implement the relaxed MDD as a global constraint that computes lower bounds and also does inference of propagation. So basically how the branch and bound procedure will look is how we see it here in the figure. We basically modify the decision diagram during the search to get a stronger bounds. In terms of experiment, we compare to 2 state-of-the-arts. We also develop a constraint programming model, and we have our 2 MDD compilations. So if we observe the results, first of all, in the blue box, we can see that both of our compilations are performing better than the state-of-the-art and the CP model, so with more instances in the time limit. But if we also incorporate our Lagrangian approach, we are solving most of the instances and outperforming everything else. So to summarize, we present an MDD-based discrete relaxation for this vehicle routing problem, the MPD-TSP, when has the MDD relaxation via Lagrangian duality. We present novel structural results and strategies for constructing relaxed MDDs, and we have an extensive numerical study where we achieve a state-of-the-art performance. So now moving to the second project, here we focus on delete-free AI planning. So the main idea is that we have an initial state, a set of operators that have preconditions and additive effects, and a cost. And the main idea is that these operators will move from one state to the other one. And the goal is to find a minimal cost plan, aka a sequence of actions that will reach all the goals starting from the initial state. So the general way to solve this problem is using a heuristic search, specifically A*, where the main idea is to create admissible heuristics that basically give us a lower bound to guide the search. And what we propose is 2 novel admissible heuristics based on relaxed DDs. So the first heuristic, here we wanted to represent the sequential aspect of the problem. So basically, in our decision diagram, the paths are going to represent the possible plans, and we develop a novel critical path heuristic over the decision diagram to compute the admissible heuristic. In contrast, we also have a BDD encoding, where here we relax the sequential aspect of the problem, so we only focus on set of operators. And now what we have is that in each layer, we have whether or not we choose an operator, and the shortest path will give us an admissible heuristic. So in terms of theoretical results, we related for the MDD, we related to other graphical structures in the AI planning community. We showed that the heuristic is admissible and consistent, and also that the heuristic dominates the H-max heuristic, a well-known heuristic in this community. And in addition, for the BDD, we show we have some insights on variable ordering, on how to create informative heuristics. We also show that the resulting heuristic is admissible and consistent, and the relationship with the disjunctive landmark heuristics in the literature. In terms of empirical results, we develop our own branch and bound search procedure for delete-free planning. We compared against a mean model inside Groovy and also its LP relaxation in our own branch and bound procedure, and over some problem instances from the IPC domain. So all in all, here is the number of instances that we saw for each of the domains. In some of the instances, we have better, in some of the domains, we have better results than the MA-ILP in Groovy. In some other ones, we have comparable results with the LP heuristic in our own branch and bound procedure, but all in all, the MIP model was performing, has a better coverage. So to summarize, we present two novel admissible heuristics for delete-free planning based on decision diagrams. We propose alternative ways to use this decision diagram to research beside the heuristic computation. We have an in-depth theoretical and numerical analysis of this heuristic. And lastly, we relate this DD-based heuristic with existing methodologies in this community. So last but not least, here I'm going to present our third project on cut generation and lifting for binary optimization problems. So in this project, we have binary optimizations of the following form. We have a linear objective function and a feasibility set that can be represented either by linear or non-linear constraints. And what we propose is a cutting plane and lifting procedure that leverages the combinatorial structure of the problem. And how do we expose this combinatorial structure is using binary decision diagrams, BDDs. So the main idea is the following for the lifting procedure. Let's assume that we have a set X and we want to find its convex hull and we have a valid inequality. So the idea is that we will use the BDD to make this inequality stronger by tilting it or rotating it so we touch more points on the convex hull. To do this, we compute what we call this disjunctive slacks, that is basically solving the problem when one of the variables is fixed to 0 or 1, and we can do this efficiently using BDDs. And basically, we show that using this DSLAC, our procedure can create a stronger valid inequalities for our set X. In addition, we present some new ways to generate cuts using the BDDs. We have a network flow. We present a new network flow polytope for a decision diagram that we show that is equivalent to the convex hull of our set X. And using this, we create a separation problem to identify whether or not a point is inside the convex hull. And thanks to this separation problem, we can generate what we call a general BDD flow cuts, basically using duality, and we show that these cuts actually define the convex hull, so they are as strong as they can get. However, we notice that solving this problem might be a little bit challenging because we have to create a huge LP depending on, of course, if the decision diagram is huge. So we also have another alternative where we relax some of the capacity constraints that we have and basically transform the polytope and the separation problem into just a max flow problem, so we can solve it directly over the decision diagram instead of creating an LP to generate the cuts. What we get in the end is what we call our combinatorial BDD flow cuts, that how we create them is using max flow and min cut duality. Here I have just a small example that unfortunately, I don't have time to explain. And I also want to emphasize, since this is a relaxation of your original separation problem, it not necessarily can cut all the fractional points. Lastly, well, we apply this technique to 0-1 chance constraints. So they're basically problems where we have a probabilistic constraint where the coefficients, in this case A, have Gaussian distribution. And then I think that we can reformulate it as a second order cone that has the following form. And the main idea on this application is that we create a one decision diagram for each of the second order cone inequalities using a recursive model. And since these constraints, the space of these constraints can be very large, the BDDs can be very large, we limited the size to only 4,000 nodes per layer. In terms of experiments, we have 270 instances. We compare against Cplex, and we tried the two different variations of cuts, the general ones and the combinatorial ones, and with and without the lifting. So here are the overall results, number of instances solved over time. And then when we reach the time limit, we have the accumulated optimality cap at the time limit. So we can see that Cplex is the one that is performing the worst. And actually our best approach, that is the stronger cuts, the general BDD cuts plus the lifting, are solving 31 more instances than Cplex and have a 42.6 average final gap reduction. So all in all, we presented a general combinatorial lifting procedure based on BDDs. We studied theoretical properties and relationship with existing methodologies. We proposed two novel cutting plane procedures defined over the BDDs. To do so, we proposed a new Pareto for the BDD and also a max flow problem over the BDD to generate cuts. And in terms of numerical analysis, we focus on chance constraint problem, where we show better performance of the state-of-the-art solvers that in this case was Cplex. So just to conclude, I wanted to give a brief overview of my thesis, my dissertation, sorry. So we present new methodologies to solve discrete optimization problems using decision diagrams and existing techniques. Here are the three projects that I presented: the multi-commodity pickup and delivery, delete-free AI planning, and the cut generation and lifting. So thank you so much for listening. If you have any questions, please don't hesitate to reach out to me. Take care. Bye.